We are beginning the numericals of exercise of the chapter number 10. First numerical 10.1. Monochromatic light of wavelength 589 nanometer is incident from air on water surface. What are the wavelength, frequency and speed of reflected and refracted light? Refractive index is given, that of water 1.33. Now see, whenever the light is reflected, then reflection is in the same medium. So this is the incident light and this is the reflected light. Then reflected light is moving or traveling in the same medium, while the refracted light will be moving in the another medium where speed and wavelength will change, frequency remains constant. Whenever the light goes from one medium to another medium, its frequency remains constant, but the speed, and wavelength and speed will change in the next medium. This is the concept. Frequency remains constant. Now it is divided or calculated into two parts. First is for the reflected light, that is in air. That is in the same medium the light is reflected. So wavelength lambda is given 589 nanometer. So medium is same, therefore the light which is reflected will have the same wavelength, it will not change, it will remain 589 nanometer. Frequency is c upon lambda. C is velocity of light, lambda we are having. If you just simplify, you will have the frequency to be 5.093 into 10 raised to 14 hertz. The speed of light that is reflected will be same as that of incident light, because the medium remains the same. Now the light ray which is refracted means now the light ray which is traveling in the water medium. Now as you know, refractive index is nothing but wavelength of light in air upon wavelength of light in medium, or wavelength of light in first medium from where the light is incident divided by wavelength of light of wavelength in the medium where the light is moving. So this is medium 1, or we can say this is the wavelength in medium 1, this is wavelength in medium 2. So it is lambda upon lambda prime, that is n. So lambda prime, that is lambda upon n. So lambda is known to you, 589. Refractive index is 1.33. So you can just calculate 442.86 nanometer will be the wavelength in the water medium where the light goes. Now frequency remains the same, it does not change with the change in medium. Speed we want to find. Now refractive index is the ratio of velocity of light in air or velocity of light in vacuum divided by velocity of light in another medium. So velocity v is equal to c upon n. So that value is written here. C is velocity of light in vacuum or air, both are nearly same, 3 into 10 raised to 8 divided by 1.33. So the speed of light in the water medium you will get, that is 2.256 into 10 raised to 8 meter per second. Now numerical number 10.3. The refractive index of glass is 1.5. 1.5. What is the speed of light in glass? Speed of light in vacuum is 3 into 10 raised to, very easy. N is equal to C upon V, that is speed of light in vacuum divided by speed of light in given medium. So V is equal to C upon N. C is 3 into 10 raised to 8 divided by 1.5. So you get 2 into 10 raised to 8 meter per second. Okay. Second question, is the speed of light in glass independent of the color of light? If not, which of the two colors, red and violet, travels slower in the glass prism? Now see, color of the light, or rather color of the light depends on the frequency. Okay, color depends on frequency. So frequency is different for different color light. Greater is the frequency, greater is the refractive index, and smaller is the speed of light. Okay, value of frequency is more, then the refractive index will be more and smaller will be the speed of light. Now frequency of blue light is greater than the red light, hence speed of blue light is smaller than that of the red light. So blue light travels slower than red light in any dispersive medium. Here we have glass medium. Okay, thus speed of light in glass is not dependent of its color or frequency. Okay, so we can say that the speed of light in glass is not independent of its color. Okay, it is not independent of its color, it is depending upon color. So different color light will have different speed in the medium of glass. Here we have prism. Okay, now we have fourth numerical. In Young's double slit experiment, the slits are separated by 0.28 mm. Okay, so distance between slits, that is distance between slit S1 and S2, which is denoted by small d, is 0.28 millimeter. Okay, and the screen is placed 1.4 meter away. So capital D, distance of the screen is 1.4 meter. The distance between the central bright fringe and the fourth bright fringe. So distance of fourth bright from central, that is x4, is given, that is 1.2 centimeter. Okay, determine the wavelength of light used in this experiment. Now for nth order bright, we have the path difference x and d upon capital D is equal to n lambda. Here n is 4, so x4d, x4 small d in divided by the capital D. Okay, divided by capital D is equal to 4 lambda for the fourth order bright. So lambda is x4d upon 4 times capital D. Now all the values are known to you. Okay, just we have to place these values. Okay, here they are converted into centimeter. Okay, so D, small d is given 0.28 millimeter. So if you want to convert it into centimeter, then it is 0.28 into 10 raised to minus 1 it becomes. That is why it is written here. Capital D is 1.4 meter. To convert it into centimeter, 1.4 into 10 raised to 2. So it becomes centimeter. So it is written here. Okay, here x4 is already given in centimeter, and that is 1.2. Okay, 1.2 centimeter. So everything is converted into centimeter, and just you simplify and you will get the value of lambda, and that lambda will be 6 into 10 raised to minus 5 centimeter. Okay, you can convert it into angstrom. Okay, so it becomes 6 into 10 raised to 3, so it becomes 6000 angstrom. Okay, now we have the fifth numerical. In Young's double slit experiment using monochromatic light of wavelength lambda. Monochromatic means it has only one color, means wavelength is only one, it is not a mixture of different color. The intensity of light at a point on the screen where path difference is lambda is k unit. So intensity where the path difference is lambda is k. What is the intensity of light at a point where the path difference is lambda by 3? Now, according to Young's double slit experiment, this intensity is given by this formula: I is equal to I0 cos square k R2 minus R1 divided by 2. Here R2 minus R1 is the path difference and it is given lambda, and intensity where the path difference is lambda is k. Okay, so instead of I we can write k. Okay, here k is written, and instead of this R2 minus R1, R2 minus R1 we have written lambda. Instead of this R2 minus R1 it is lambda. And as you know that wave vector k, this k which is appearing here, k, that is nothing but, okay, that k is 2 pi upon lambda. So these values are substituted here. Okay, instead of this small k it is 2 pi by lambda. R2 minus R1 is lambda, and this 2 remains in the denominator. So this 2 will be cancelled out, this lambda will also be cancelled out. You will have cos square pi, and cos square pi, cos pi is minus 1, square of it will give you positive 1. So intensity I0, that is initial intensity, is equal to k, that we are getting from this result. Now second point is given where path difference is lambda by 3. So R2 minus R1 is taken as lambda by 3. Okay, k is again 2 pi by lambda, this everything is same. So it becomes, if you simplify, then you will get pi upon 3, because this 2 and 2 will be cancelled out, lambda will be cancelled out. We will have cos pi by 3, cos pi by 3 is 1 by 2, and square of it, because here it is cos square, so square of 1 by 2 will be 1 by 4. Okay, and I0 is already with us, that is k. So if you place the value, okay, and simplify, then that intensity where the path difference is lambda by 3, then intensity at that point is found to be k by 4. Now numerical number 10.6, a beam of light consisting of two wavelengths. So the beam is having two wavelengths, it's not a monochromatic source, we can say 650 nanometer and 520 nanometer. It is used to obtain interference fringe in Young's double slit experiment. Find the distance of x3 fringe on the screen from the central maximum of wavelength 650 nanometer. What is the least distance from the central maximum where the bright fringe is due to both the wavelength coincide? Now see, different values are given to us. Okay, these values are to be taken like this: small d, that is distance between S1 and S2 is 2 millimeter, 2 into 10 raised to minus 3 meter. Okay, these values are not mentioned, but we have to take these values. Okay, capital D is 1.2 meter, lambda 1, lambda 2, both the wavelengths are given. Okay. Now for third bright, it is mentioned in the first question that x3 fringe on the screen. Now that is not clear whether it is barabar maxima or minima, but here we have to consider it as a maximum. Okay, not mentioned, but that should be mentioned. Okay, for third bright, as you know, path difference is n lambda for general purpose formula. So x3, okay, n is 3. For third bright, n is 3. So x3d upon capital D is equal to 3 lambda. So x3 will be 3 lambda capital D upon small d. All the values are with you. This calculation is for the 650 nanometer light. So instead of lambda, we will write 650 into 10 raised to minus 9. Then capital D, okay, it is in 1.2 meters, so 120 centimeter into 10 raised to minus 2. Just for the sake of calculation, it has been converted like this. 2 into 10 raised to minus 3, just simplify, we will get the value of x3, 1.17, 10 to the power minus 3 meter. Now suppose minimum distance required is x, where n1 and n2 order of bright fringes of the lights with the wavelength lambda 1 and lambda 2 respectively coincide. Try to understand. You have, say, the interference pattern which are produced on the screen. Well, this is central maxima, then this becomes the minimum, and again central maxima. Now the distance at which, say for example, this distance is x from the central maxima, where the fringes, or we can say bright fringe of first and second wavelength coincide. Say for example, this is the place where the two bright fringes of two different wavelengths, or we can say bright fringes of two different wavelengths are getting coincide, and this distance is x from the central maxima. This distance is, say, x. Okay. Now then what will happen? For the first wavelength, let the number of fringe is n1, or we can say n1th fringe of first wavelength is produced here at this point, and n2, or we can say n2th fringe of second wavelength is produced here, and they are getting coincide at a distance x from the central maximum. So x is same, the distance of both the bright fringes which are getting coincide is same from the central maxima. So in general we have the formula xd upon capital D is n lambda. Now here x is same for both, because the distance at which they are getting coincide, the distance x is same. The s1 s2, that is distance between the two slits, that is d is same. The distance of the screen is also same. Here it becomes n lambda. Okay, and this part become constant irrespective of wavelength. Okay, because the two fringes are getting coincide. So n lambda is constant, we can say n lambda is constant. So we can say n1 lambda 1 is equal to n2 lambda 2. Now n1 upon n2 you can find by taking lambda 2 upon lambda 1, and that can be 4 upon 5 easily, it can be obtained. 520 divided by 650. Okay. So n1 is 4, or we can say fourth bright fringe of first wavelength and fifth bright fringe of second wavelength are getting coincide. Now you can use x d by d is equal to 4 lambda, then we have to take 4 lambda 1, or we can take x d by d, then you take, say, 5 lambda 1, whichever, but the answer will be same. at that time you have to take phi lambda 2. Try to understand whichever wavelength that you are taking corresponding n we have to take into consideration. So xd by d is equal to 4 lambda 1 you can take, and you can find the value of x, or we can take xd by capital D is equal to 5 lambda 2, and you find the value of x. Both the way you will get the same value of x, because these wavelengths are getting coincide at distance x. Coincide means the distance is same from the central bright fringe. Okay, so any one you can take. Xd by capital D is 4 lambda 1, say for example we have taken. Okay, so x is equal to 4 lambda 1 capital D upon small d. Just place the values. Okay, lambda 1 is 650 10 to the power minus 9, capital D is 1.2 meter, that is 120 into 10 raised to minus 2 you can write. Small d 2 into 10 raised to minus 3. So x is equal to 1.56 into 10 to the power minus 3 meter you are getting. Okay. Similarly, if you take 5 lambda 2, then also the answer will be same only. You can see both the answer, both the way you can calculate, any one you have to calculate. Okay. Now numerical number 10.8, what is the Brewster angle for air to glass transition? Refractive index of glass with respect to air is 1.5. Now it's very easy. As you know, tan theta p is refractive index of glass with respect to air, or we can say mu Ga. Okay, this can be written. So refractive index of glass upon refractive index of air. So tan theta p is 1.5. Just we have to look into the natural tangent and find the value of 1.5. It is about 56 degree 19 minute. Okay, or we can say about 56.3 degree. Okay. Now numerical number 10.9, light of wavelength 5000 angstrom falls on the plane reflecting surface. What are the wavelength and frequency of the reflected light? What are the wavelength and frequency of the reflected light? For the angle of incidence is the reflected ray normal to the incident ray. For what angle? For what angle of incidence is the reflected ray normal to the incident ray? Now see, wavelength is given, frequency easily can be found. Okay, C is equal to nu into lambda. So nu can be C by lambda. Here instead of nu it is taken as F, whichever. Okay, so it is 6 into 10 raised to 14 hertz. Okay, now it is given that angle of incidence and angle of reflection, they are perpendicular to each other. So I is I plus R, that is angle of incidence plus angle of reflection. Angle of incidence plus angle of reflection is 90 degree. Try to understand. For what angle of incidence is reflected ray is normal? So incident angle plus reflection angle is 90 degree. So angle of incidence plus angle of reflection is 90. Now as you know from the laws of reflection, angle of incidence is equal to angle of reflection. So instead of R we can write I. So it becomes 2 times I is equal to 90. So incident angle will be equal to 45. Okay. Thank you very much. Calculate all the numericals 2-3 times in your notebook. Okay.